Good afternoon. Going back to what we have been dealing with in case of one-to-one functions and their inverses, and we looked at operations involving functions, polynomial as well as rational, and then we looked into briefly exponential functions, and again, just for what we have in the general case, okay, we have like an exponential function, okay, where we have like y is equal to f of x is equal to a to the x. And for the restrictions upon an exponential function, okay, that has a single exponential term, again, the exponential base is going to be a positive value except for 1. And again, just for the restrictions, okay, we have for whatever the value of y is, if we have a single exponential term in the form of a to the x, whatever the value of y is, it has to be positive, as denoted by y is greater than 0. And that is going to go ahead and define the range of the function where we have those values y greater than 0. And for what we have in the case of x, okay, we can plug in any value for x in the real number system, whether the value is negative or 0 or positive. So for the domain of f of x, we have all real numbers. And the domain we have, again, from negative to positive infinity. And for what we have in the case of the inverse, remember, a one-to-one function and its inverse will have interchanging x and y values. So for what we have in the case of x, for the one-to-one function, we're going to have ny in the inverse. Okay, so the domain of the exponential function is going to be the range of what we have in the inverse. And if we invert the language, now again, we have that y or f of x is greater than 0 in the exponential function, and the range is going to be what we have in x for the inverse. Okay, so we will have the values of x that are positive for x in the inverse. And again, for the inverse function, again, interchanging the x and the y terms. Okay, so we're transforming y is equal to a to the x over to x is equal to a to the y. And so we have, again, taking care of the exponential base a, we're looking at taking the base a logarithms of both sides. And so we have the base a logarithm of x is equal to the base a logarithm of a to the y. And we're going to have the bases, logarithmic and exponential, to cancel out. So we have the right-hand side, okay, to be what was the power in this case, which you have at y, and we have in the rewrite, okay, so you had y is equal to the base a logarithm of x, and again, just formally stating in terms of an inverse function, we come out to the inverse of f of x is equal to the base a logarithm of x. Okay, so again, by definition, a logarithm is going to be the inverse of an exponential function. And just looking at what we have in the case of taking examples of what we have in the mix. Okay, and let's say if we have okay, so if I were to determine the inverse of the following, I'm going to include, okay, the domain and the range of everything, the one-to-one as well as the inverse. Okay, so if I have, just for starters, okay, so if I'm looking for the inverse, let's say y is equal to f of x is equal to 3 to the x. Okay, and now just some things to start out with. Okay, so you have f of x is equal to 3 to the x. Okay, so we have a single exponential term. Okay, so you have like in the format of y is equal to a to the x. Okay, so your a value is at 3, and again, a is at 3, it is positive, and it does not equal to 1, And again, we can plug in anything for x, and we can say that for f of x equal to 3 to the x. Again, so you have, for the same reason, you can plug in any value for x. So the domain of f of x will be the set of all real numbers and again, for the range, okay, so whatever I have for 3 to the x, regardless of whether x is negative, 0, or positive, 3 to the x is going to stay positive. Okay, so just keep that in mind. Okay, so you're going to have, again, that y is greater than 0. Okay, and so that is going to come to define the range of this function once again. Okay, so you have for the range of f of x, okay, have those values of y which are going to be positive. Yes?
So the range is, you said all real value, all real numbers?
The domain, okay, the domain is going to be the set of all real numbers. Like I can give you just a case. All right, say if we have like x, yeah, y is equal to 3 to the x. Okay, and say if we have like x is, we'll say negative 3. And like 3 to the negative 3, that's going to be like 1 over 3 cubed. So that's going to be 127. Okay, and it's going to be a small positive number, but still a positive. So you have like your order pair would be like negative 3, 127th. And say if I have x is 0, you have like 3 to the 0 is equal to 1. And so your order pair in this case would be 0, 1. And let's say if I have like x is at 4, your y value will be at 3 to the 4th, which would be 81. And so you have for this order pair, you will have like 4 and 81. And I'll just mention, like if I have x is at negative 6, let's say, your y value will be like 3 to the negative 6th. And 1 over 3 to the 6th. Now this is going to be a very small number. And now for x, so I can plug in any negative, 0, or positive real value and come out to a defined expression for the function. And notice for the output in y, okay, so whenever x is negative, your y comes out to small fractions, but you're still positive. And so that's the reason that y is going to have the arrangement such that the range is going to be positive values throughout. And if I, so the domain, what you're plugging in for x, it could be any negative, 0, or positive value. And the output y, regardless of how negative you make x or how positive you make x, y is still going to come out to a positive value. Okay, and so now like in the case of negative values for x, your y is going to be a very small positive value more than likely, but it's still going to be a number that is greater than 0. And with the domain and the range laid out, okay, now if I were to look at the inverse, all right, now remember, we have interchanging x and y values, so the range of the exponential function, we have those values positive. Well, guess what? For the domain of the inverse, it'll be what we had in the range for the original function. And for the range of the inverse, okay, that is going to be the set of all real numbers. Yes.
I'm sorry.
Uh-huh.
I'm just confused because when I was doing the Alex homework, there were a bunch of problems, and I tried to do them this way, but the domain came out to be something totally different because I had to do the inverse first, and then determine the range and domain from that.
Okay. Okay. What's going to happen? I'm going to give you some cases here, and probably the exponential functions you dealt with had like an additional operation, and I'm going to mention that in just a moment. Okay, so we got the domains and the ranges, and now in looking at the determination of the inverse, okay, so we got our function that f of x is equal to 3 to the x. Okay, so we have y is equal to 3 to the x. Okay, and after looking at interchanging x and y, okay, so we'll have in the rewrite, okay, so we'll have the x is equal to 3 to the y. And what's going to happen here, okay, is that to free up y, okay, now your base a is going to be a base 3. So if we take logarithms and base 3 and apply it to both ends, okay, so you have a base 3 logarithm of x is equal to the base 3 logarithm of 3 to the y. Okay, so I have the base 3 logarithm of x is equal to y. And we have that y is equal to the base 3 logarithm of x and so we'll have for the inverse function, again we'll have the base 3 logarithm of x. And so looking at what we have here, so we start out with the exponential function. And just for what you have in the illustration, now a lot of the scientific calculators will not have like a base 3 logarithm or anything that's outside natural and base 10 logarithms. But I'm going to show a formula where you can look at some of the conversions that we have, say going from natural or base 10 logarithms to logarithms of other bases. And for what we have in the case of y is equal to 3 to the x, okay, so you have like when x is 0, we got 3 to the 0 is 1. When x is 1, we got y is equal to 3 to the first, which is 3. And when x is 2, okay, we have y is equal to 3 squared, which is 9. And then we have with the base 3 logarithm, okay, it's going to have the opposite effect, well, in terms of the xy arrangement. So if I switch around the values, we'll have 9, 2, 3, 1, and 1, 0. And you're going to have in green what is going to be this base 3 logarithmic curve. And again, both graphs will mirror each other about the line y is equal to x. Okay, so this is a sketch of what we have in the case of this one-to-one function and its inverse. Now, let's say that without changing things up too much. And just kind of using as a basis or the foundation what we have had with 3 to the x. Kind of doing a partial reset. I'm going to do here, I'm just going to modify this function. But I'm still going to keep the exponential base and term at 3 to the x. And let's say that if I have that y is equal to f of x is equal to 3 to the x minus 1. Okay. Now for what I had before, when I had 3 to the x, okay, whatever I have for y, in this case 3 to the x. Now the smallest value that 3 to the x can possibly be is going to be like the smallest possible value greater than 0. But now with 3 to the x minus 1, think of it like this. You have like the smallest possible positive value. And if I take 1 away from this, okay, it's because of the minus 1, we're now going to have for the output y, instead of y being greater than 0, you have what's going to be greater than negative 1. And it's because of the minus 1 that's going to follow. And I'm still able to plug in any value for x. Okay, so you have for the domain, okay, you have the set of all real numbers. Now for the range, okay, because y is greater than negative 1, you will have for the range in this particular function, okay, so you have values of y greater than negative 1. And this will carry over to what we have for x in the inverse. We have those values of x greater than negative 1. So again, y is in x for the one-to-one, we're having y for the other, and vice versa. Okay, now, in looking at what we have with this slight change up. And so we're going to have here, so you have f of x is equal to 3 to the x minus 1. Let's say y is equal to 3 to the x minus 1. And again, if I interchange x and y, okay, so I have x is equal to 3 to the y minus 1. And if I look at isolating, okay, the exponential base term, 3 to the y. So I'm going to add 1 to both sides. Okay, so I have the x plus 1 is equal to 3 to the y. And looking at taking the base 3 logarithm of both sides. Okay, so I had the base 3 logarithm of the quantity of x plus 1. Okay, so that is equal to y. And just switching around, so I have y is equal to the base 3 logarithm of the quantity of x plus 1, and we have with the inverse. Okay, so the inverse of what we have for y is equal to 3 to the x minus 1, that's going to be y is equal to the base 3 logarithm of x plus 1. And let me give you just a bit of a visual here. Okay. So if we have like x is 0, we have for y, we have 3 to the 0 minus 1. And 3 to the 0 is 1 minus 1. And so we're going to have for the corresponding y value, okay, have it 0. So you're going to have a point on the graph. And that's going to be the origin. And if I go to x equal to 1, okay, so we have 3 to the first minus 1. 3 to the first is 3 minus 1. That is equal to 2. And I could continue like if I have x at 2. Yeah, 3 to the second minus 1. 3 squared is 9. Minus 1 is 8. So you have like other order pairs you have at 1, 2. As well as 2, 8. And just looking at how this curve is going to appear. Okay, so for the curve we have in red, okay, so you have among your points, okay, you've got the origin. You got the origin point, you got 1, 2, now say you have 2, 8 among many other points. And again, for the logarithmic function, again, the base 3 logarithm of the quantity of x plus 1, you have among the order pairs. Okay, so you have 8, 2, 2, 1, as well as the origin. Okay, and so that is how this function is going to appear. And again, both functions do mirror each other about the line y is equal to x. Right. And now and for what we have now, okay, let's say that just with still centered around 3 to the x. I can do yet another modification. Let's say if I had that y is equal to 3 to the x plus 5. Okay, think of 3 to the x, yeah, y is greater than 0. But once I tack on, let's say 5, we have a positive vertical shift. Okay, this time I'll be stressing that y is greater than 5. And so for the range of the function, we have those values y greater than 5. In the inverse, we have those values x greater than 5. And as for what we have in the case of the inverse, okay, so you have f of x, okay, so you have is equal to 3 to the x plus 5. Yeah, y is equal to 3 to the x plus 5. And if we look at interchanging x and y, and I get the x, so I got the x by itself, so I have x is equal to 3 to the y plus 5. And if I get the 3 to the y term by itself, Okay, so if I take 5 away from both sides, okay, so we have x minus 5, okay, is equal to 3 to the y. And if I take the base 3 logarithm of both sides, okay, so left-hand side, here we have our base 3 logarithmic term already laid out. And to the right, I have base 3 logarithm of 3 to the y, that becomes y. And so we're going to have this inverse function. And so we're going to have for the inverse, so we have the inverse of f of x is equal to the base 3 logarithm of the quantity of x minus 5. Okay. And so for 3 to the x plus 5, okay, remember, okay, you have 3 to the 0, so you got like 0, 1, 2, 3. Now remember, non-zero number to the 0 power is 1, and if I add 5, I got 6. I got 0, 6. 3 to the 1 is 3. Add 5, I get 8. Again, 3 squared is 9. 9 plus 5 is 14. And then we have with x at 3, we've got 3 to the third is 27. 27 plus 5 comes out to 32. Okay, so you have this resulting exponential curve. And again, for the inverse, again, they're going to have, okay, mirroring the exponential curve across the line y is equal to x. And again, you have switched around x and y values. Okay, so you have 32, 3, 14, 2, and countering 1, 8. Okay, we have 8, 1. And in the case of the y-intercept, we have with the exponential curve, we have in contrast, we have the x-intercept location at 6, 0. Okay, so again, a logarithm is going to be the inverse of an exponential function. And now, looking at what we have in the group of problems, okay, that we have in reference, okay, to what we have from page 378, and we have okay, these items, okay, have by and large, okay, up until you get to the last frequency. Again, this is our compound interest formula for the frequencies, okay, that are non-continuous. Okay, so you have p times the quantity of 1 plus r over n raised to the r times t power. Okay, and for what we have in the case of the layout, let's see, just for what we have in the group, okay, and we have from page 378, and I have with the numbers. Okay, and so we got for the principal, let's see, that is yes, that was in number 46. And we have with the numbers. Okay, so we got the principal is at $8,000. And for what we have in the case of the rate of interest, okay, so that is going to be at 3.5%. And again, to be able to compute the future value, okay, we had to convert the percentage rate into a non-percent decimal. Okay, so 3.5%, okay, that becomes 0.035. And for the time span, okay, we're looking at a 20-year plan. All right. So we have in the setup here. So this is our formula between the annual and the daily compounding. Okay, so looking at what we have now. Okay, so starting out with annual compounding. We'll probably have n is equal to 1. And looking at specifying our values, okay, so you have P is at $8,000. You have times the quantity, okay, so you got 1 plus $0.035 over 1. And we're looking at 1 time a year for 20 years. And just taking what we have now. Okay, so you have $8,000. Okay, so once you add up, you got 0.035 over 1, and we have added to 1. Okay, so we'll have 1.035 to the 20th. And just looking at what we have now. Okay, so for taking 1.035 to the 20th, again, for a lot of models, you might have the caret symbol in many of the TI models, and then for some of the other scientific calculators like Casio, Texas Instruments, you might have a secondary function that applies to exponents, and it might be in the form of y to the x or even x to the y. So it's going to be one of those characters involved. And looking at what we have now. Okay, so looking at what we have concerning 1.035 to the 20th. Let's see, get my calculator. Okay, so 1.035 to the 20th. Okay, so you have a number that's going to be just under 2. And among the first digits, okay, so we have 1.9897. I can let, again, just whatever result you have, just keep it. Just let the, say if you got like 12 decimal places in your calculator, just let it carry on out, and then multiplying by 8,000. Once you get to the currency, you're going to round to the nearest 2 decimal places, like in dollars and cents terms. Okay, so for what we have, we'll come out to 15,918.31. Let's see what we have in case of annual compounding. And then for the next frequency, okay, so we're going from annual to quarterly compounding. Okay, so you have that n is equal to 4. Now with a change up in the frequency. Okay, so we've got the same foundational formula, and n is going to change. Okay, so with annual I had 1 before. Now with quarterly, we'll have 4 for n. just taking what we have now. So we got the sum here. Okay, so we'll have 1.00875. Okay, so the sum is smaller, but the power is going to be larger. Okay, so instead of 20, we'll have 4 times 20, which will be 80. And for this number to the 80th power, okay, so we have crossing the threshold, surpassing the number 2. Okay, so we have 2.00763 among the first digits. And let those be carried on out, and multiplying the result by 8,000. Okay, so we'll come out to the future value, and this will be over $16,000. And for my figure, okay, have right at $16,061 and 10 nearest penny 5 cents. And then increasing the frequency. Okay, so going from annual to quarterly to monthly compounding. And so we're going to have here, okay, so the end value again is going to be at 12. Okay, and there will be some things that will be going counter currently. Okay, so we got the sum is going to be getting smaller, while the exponent is going to be getting larger. Okay, so if I take 1 plus 0.035 over 12, okay, and this one came, we're not going to have a terminating decimal, which we have like 1.0029166, and this will be to the 240th power. Okay, so the sum is getting smaller while the power is getting much larger. And for this number to the 240th power, okay, so you have just over 2.01. And multiplying by $8,000. Okay, and so we had the balance is going to be a little bit higher. In this case, we will come out to $16,093.62. And then for crossing over into the daily compounding. So you're looking into the pretty much the maximum threshold of using our formula that we have in identifying the future value without continuous compounding. So we have with this setup, okay, so the principal is still at $8,000. Okay, the time span is still 20 years, and the quoted percentage rate we have at 3.5%. Okay, and now for N, okay, now we got a small decimal number to begin with, and it's about to get a lot smaller because we're looking at division by 365, and for the N times T, about 365 times 20. And looking at what we have with the decimal. Okay, so you have 1.035 over 365. If you add to 1, then you have, after the leading 1, you have like 4 zeros. You have like 9589. And you have 365 times 20, so this would be 7,300. Okay, so it's like the higher the power gets, it's like the lower of what you're adding to 1 becomes. Okay, and this is almost like adding almost nothing to 1. But that little bit, especially to such a large power, okay, is going to accumulate to a little bit of a difference. And so we have for this number, okay, so we come out to about 2.0136. And multiplying by $8,000. Okay, so we have to the nearest cent, okay, have right at 16,109.48. Okay, so for, oops. I don't know what happened here. Let me do something right fast. Okay, so just looking at what we have for the items here. So annual compounding, you have 15.9, 18.31. Quarterly, we have 16.0, 61.05. Okay, balance is a little bit higher. And then once we get to monthly, okay, you have almost about a 31, between $31 and $32 in the jump, a little bit higher. And then for daily, okay, you have 16.109.48, still a little bit higher. And in terms of attaining the maximum threshold, and this is what we're going to have in the case of continuous compounding. Okay, and so, okay, just a reminder. Okay, so we have for A is equal to P times the quantity. Okay, we have a 1 plus R over N to the N times T power. Okay, we've had the values to get larger and larger. Okay, from annually at 1 to daily at 365. And as N approaches infinity, we have for this particular formula, okay, this statement is going to become A is equal to P times E raised to the R times T power. Okay, so we have with the remaining category, okay, so we have with continuous compounding. Okay, so in this particular case, right, you can put down either response for the N value. You can say you have either not applicable in terms of, we don't have a finite value, or you just have approaching infinity. Right, and so for what we have in the case of the balance, you can say have A is equal to P times E raised to the R times T power. So P we have at $8,000, and you have times E and the rate we have at 0.035, and the time span we have for 20 years. Okay. Now, while there are fewer characters to work with, okay, you still have to be careful, especially if your calculator does not have the order of operations. So if you're working with E, okay, you want to go ahead and take the product of the rates and the time. So 0.035 times 20, okay, so that's going to be 0.70. And for what we have in the case of E to the 0.7, so for this decimal also above 2.013. And we have multiplying by $8,000. Okay, and we have for the theoretically maximum attainable future value. Okay, this is going to be right at $16,110 and about 2 cents. Okay. So you have with the 3.5%, you have at the minimum side in terms of how the 3.5% is applied with the same dollar figure and the time span. You have the annual, you have 15/9/1831, 20 years from now. But in the case of the theoretically maximum, where you had the 3.5% applied continuously, non-stop, you had the future value balance after 20 years, okay, right at 16,110.02. Okay, so a little bit of a difference here. All right, now where we have regarding the application of interest, okay, and we have just differing rates in the case of looking at continuous compounding, and we have for the case in number 48. Okay, and here, okay, now we got we have a given principal at $6,000, and the time span is 12 years. And looking at what we have for the future values. Okay, so we have in the case of part A, okay, so we're looking at the future value whenever R is at 1%. Okay, so we have as a decimal. Okay, so 1% is going to be 0.01. Okay, so just filling in the numbers. Okay, so you got $6,000. And for E to the R times T, so R is at 0.01. And the time span we have for 12 years. And for 0.01 times 12, okay, so we're looking at E to the 0.12. Again, E is that 2.718 figure. Now for E to the 0.12, Okay, so we're looking at right at 1.1274. And multiplying by $6,000. And for the number here, okay, so it would come out right to $6,764.98. And if I change up the percentage rate, okay, so at R is equal to 2%. Okay, so to be able to take the computation, okay, so we convert from percent to non-percent decimal. So R is going to be at 0.02. Okay, so you still have the same principal and time. Okay, so for the product between the rate and the time, okay, so that's going to be 0.24. And so for e to the 0.24, okay, so we have 1.27. 124. And keeping that result and multiplying by 6,000. Okay, so we're looking at 7,627.49. Okay, so if when I went from A to B, I doubled the percentage rate. And let's say if we do a little bit more as we go from part B to part C. Okay, so we got all the way out to 4.5%. Okay, so as a decimal, okay, we're looking at 0.045. So we have with compounding of interest for 12 years at 4.5% with a principal of $6,000, and looking at attaining the future value. Okay, so I have $6,000, and for R times T, okay, so that's going to be 0.54. And for this number, okay, so we got just over 1.7. And for this result, okay, so I'm going to cross over to not just over $8,000 or $9,000, but also over $10,000. And so for this balance, it's going to come out to $10,296.04. So those are cases of what we have exclusively with use of continuous compounding of interest. Now, in terms of what we have in looking at comparing deals, and we have in the case number 49, okay, we're looking at Bethany, and she is looking at borrowing $10,000, and she has two options in terms of how to go about financing. Okay, the first option is that she can borrow the money at 5.5% simple interest for 4 years, or as the other option, she can borrow at 5% with interest compounded continuously for 4 years. Okay, and looking at comparing and contrasting, okay, the resulting interest, okay, with the options. Okay, now we're looking at part A. Okay, how much interest Bethany would pay at 5.5% simple interest. Okay, so we have, in the case of simple interest, okay, so on the side of simple interest, okay, so have I is equal to PRT and again, the principal is what she is borrowing. And again, for the rate of interest, okay, the quoted percentage rate. Okay, about 5.5%. Again, just writing it as a non-percent decimal. So we'll come out to 0.055. And we're looking at, for the time span, we're looking at a 4-year plan. And so for the amount of interest, okay, so you got the principal, so you have it $10,000. We got the rate R, again, that's a non-percent decimal value, so you have 0.055. And again, we have a 4-year plan. Okay. So for Bethany, if she goes with the simple interest option with the 4-year plan, and you have simple interest with the rate at 5.5%, she's looking at facing an interest amount of $2,200. So in her case, okay, if she's borrowing $10,000 and winds up paying back in full, she'll end up paying $12,200, namely the $10,000 in interest, $10,000 borrowed plus the $2,200 in interest. Okay, now for what we have in the case of the compound interest option, so we have this line up. Okay, so you still have P. At $10,000. Okay, and for the rate, okay, that's at 5%. So that's going to be 0.05. Again, we have the time span is going to be for 4 years. Okay, and if Bethany had the simple interest option as opposed to a compound interest where the rate is 5%, same arrangement, the 5% deal would definitely be that which would result in less interest. But with the compound interest, okay, that is that other formula. We have P times Z to the R times T, and we're looking at on a continuous basis. Okay, so what we have compounding continuously. Okay, so you have P times Z to the R times T. So P we have at $10,000. You have times E, and you have raised to the R times T. Yeah, with the numbers. Okay, so this time we have e to the r times t, and the product is going to be 0.20. And so we have with the numbers. So e to the 0.2, okay, so I have right at 1.2214. And multiplying by $10,000. Okay, so looking at right at $12,214, and to nearest penny, this will be about 3 cents. Okay, so looking at the total on this one. Okay, so you got $2,200 in interest, and with the future value with the continuous compounding, you're going to have that the interest from this is going to be the difference between the future value and what was borrowed. Okay, so for the value A, we have it 12,214.03. We're going to have minus the $10,000 borrowed. And the difference here, we have it 2,214.03. Okay, so that will be the amount of interest with that particular plan. Okay, and we have just for the lead in to what we have for part C. And it's asking, okay, it's like which option results in less total interest. And if you look at the options here, simple interest, you have $2,200, and then with the continuous compounding of interest, you got 2214.03. And between the options, okay, it turns out that even in spite of the 5.5% interest, the way the 5.5% is applied turns out to be less than the 5% that was applied in the realm of continuous compounding. So you can say that the simple interest option results in less interest. Okay, the difference you have about $14.03. All right. Now, and we will be looking into applications further, okay, working with interest and other avenues, okay, which we go about compounding the numbers, and now again, just going back to what we have with working with logarithms, okay, and again we have the letter E, that is the natural logarithmic exponential base, and this is going to be involved with some of the applications we will have with logarithms. And sort of crossing over to the threshold of looking at the properties of logarithms. Okay, so they're going to have their own kind of functioning outside of just being the inverse of an exponential function, and just some of the things we have in the foundation. And for what we have in the case, properties of logarithms. Okay. And this is going to be reminiscent of when we looked into like matching bases in the logarithmic and exponential terms. Okay, so you have like first property, if you have a base A logarithm of a to the x, okay, that is going to be equal to x. Okay, so you have a match between the logarithmic and exponential base. Okay, whatever raised power there is, that is going to be the result. Now let's say that if we have let's say we have like I'm using calculator notation. Say if I have log of 100. Again, in calculators, okay, log is going to make reference to a base 10 logarithm. Now, we don't have a match yet, okay, but think about 100 relative to 10. Okay, 100 is a multiple of 10, and it also happens to be an integer power of 10. So like 100, okay, that's going to be 10 times 10, and in exponential terms, so 100 is going to be 10 raised to the second. So in this rewrite, we're going to have that a is at 10 and x is at 2. And so we have the base 10 logarithm of 10 to the second. Okay, that reduces to 2. Now say we have like ln. Now say we have of e to the negative 4. Okay, so you got ln. Okay, so in your calculator, okay, so ln is going to make reference to a base e logarithm. And the natural log of e to the negative 4 is going to be the base e logarithm of e to the negative 4. And again, so you have in this property, a is represented by e and x by negative 4. And so we have for this outcome, okay, this will be at minus 4. Now let's say we have something like a base 5 logarithm of 125. Now for what we have here, for a base 5 logarithm of 125, okay, just like 100 is both a multiple and integer power of 10, then we had that 125 is likewise, okay, going to be a multiple and an integer power of 5. Okay, so like 5 times 5 is 25, times 5 is 125. Okay, so 125 is 5 cubed. And so rewriting this to where we have the matching exponential logarithmic bases. Here a is represented by 5 and x is at 3. And so 3 is going to be the outcome in this one. All right. Okay. And for the initial exponential logarithmic equations, and once we get into sums and differences of logarithms, you'll see this property quite a bit. And for the next property, which will be very much akin to this, you won't see this quite so much until we get to the last bit where we have working with logarithmic equations. And if you have in this one just kind of rewriting, okay, so I have a base a logarithm of a to the x is equal to x. But if I have, let's say, the exponential base a, and the power is the base a logarithm of x, that is also going to reduce to x. And just some of the instances here, if I have, let's say, I have like something like 2 to the base 2 logarithm of 16. You have 2 to the base 2 logarithm of 16. That's right, your a is at 2. Base a logarithm is a base 2 logarithm, and x is represented by 16. So that is equal to 16. If I have like e to the ln, or natural log of 14. Again, ln, or natural log, is going to be a base e logarithm. Okay, so a is represented by e, and here x is represented by 14. If I have 10 to the log of 3, so log is going to make reference to a base 10 logarithm. So 10 to the base 10 logarithm of 3. Okay, so that is going to be equal to 3. Now, in terms of numbers, I had mentioned from the start, okay, it's like chances are you're not going to have like a base 3 logarithm in your calculator. You might have just the natural and base 10 logarithms. And for the next property, you're going to have what's referred to as the change of base formula. And this is going to state, okay, see if you, regardless of whether or not you have a match between the exponential and logarithmic bases. Let's say that especially if you don't have a match, okay, let's say that if you have like trying to determine the base a logarithm of m, and let's say that you don't have that base a logarithm in your calculator, okay, there is an item, and with the change of base formula, we can go with the secondary logarithmic base, and for the base a logarithm of m, we go with the secondary logarithmic base. We have like a base b logarithm of the attachment is divided by the base b logarithm, and then taking that of making the attachment of what was the original logarithmic base, in this case, which we had at a. And for the base b logarithm, at least in terms of the common scientific calculators, you could say it could be the natural logarithm of m over the natural logarithm of a you go with either ln, or you go with log, base 10 logarithm of m over the base 10 logarithm of a. Doesn't really matter which set you use, you still want to have the same decimal result. And we can say that, say we're looking at, say, rounding to about the nearest 3 places. Okay, see if I have something like let's say a base 3 logarithm of 77. So you got a base 3 logarithm of 77. So here, a is represented by 3, m by 77. And looking at taking what we have now. Okay, so m is at 77, a is at 3. And I can go with either natural or base 10 logarithms. I'll just go with natural logarithm on this one. If you enter into your calculator, you'll have to enter ln twice. So here we have the natural logarithm of 77 all over the natural logarithm of 3, and say to about the nearest 3 decimal places. Okay, so that's going to be about a 3.954. And if we have something like, give you like a decimal. Say if I have something like a logarithm, okay, where the base, we say is going to be like 0.4. And I'm taking this, we'll say 46. Okay, so A is at 4/10, and M we have at 46. And I can go with Ln once again, but if I go with log, so we have the base 10 logarithm of 46 all over the base 10 logarithm of 4/10. Now for this number, okay, this is going to be a negative quantity. We'll have right at negative 4.178. We have with the remaining property, okay. And this is also especially if you don't have a match between the logarithmic and exponential base. If I have something like the base A logarithm of m to the r, and this will carry over to the sum and difference formulas. Okay, if you have a raised power, okay, and you don't have a match between the exponential and logarithmic bases, you can convert that power to a coefficient. In this case, we have r times the base A logarithm of m, and we say that if we have something like let's say the base 5 logarithm of t to the second. And I rewrote this, okay, so your r is represented by 2, and your base A logarithm is going to be base 5 logarithm, and the attachment m we're going to have in this case at t, so you have 2 times the base 5 logarithm of t. And let me mention this remaining part here, especially if you have like a binomial expression or a polynomial. Now say you have a base 7 logarithm of 31 to the b plus 4 degree. Right. So you got A represented by 7, M by 31, and R is represented by the 2-term expression b plus 4. And if I shift b plus 4 over to the front, okay, now all of r is going to be multiplying the base A logarithm of m. And so to have b plus 4, everything multiplying the logarithmic expression, I'm going to need parentheses over here. So we have all of b plus 4 times, okay, the base 7 logarithm of 31. So let me just mention, okay, so you have we need parentheses in this case, because if I leave out the parentheses, it's going to look at b separate from 4 times the base 7 logarithm of 31. But I'm looking at this logarithmic attachment being multiplied by both terms b plus 4.